of all, I'd like to thank the organizers for the invitation. It's a great pleasure to be here in this very nice conference. My name is Olcyr. I work in Padova, and today I'm going to continue the discussion on the bit physics anomalies and their implications. This presentation will be based on these two papers. The first one in collaboration with my colleagues in Padova, and Paradisi. And the second part is based on this collaboration with people in Norse and Ljubljana. So we just had a very nice overview talk by Andreas. So let me just remind you what the situation is. Over the past 5-6 years, we had a lot of excitement in the flavor physics community. And that was mostly thanks to the measurement of these ratios of beam mass decays. And what was very interesting is that we saw a pattern of deviations in both in process that appear at tree level in the standard model and also at loop level. And in particular, all these observables, they are related to the same physics idea, the one that we are observing new sources of lepton flavor universality. So this is what I'm going to talk about. I'll be mostly interested about the implications of these results. In the first part, I'm going to talk about model-independent conclusions that you can derive by using effective field theory with a very minimal set of assumptions. And in the second part, I'm going to talk about one specific model that can accommodate all of this data and which also has very nice signatures to be tested in current experiments. So let's start with the EFT implications, and then I'm going to talk about these RD and RD stars. The reason will be clear in a second. So as Andreas said, this is a B2C lepton neutrino transition that in the standard model is mediated just by a downward exchange. So the situation is that you have measurements by both bit factories and LHCb. We have seen several deviations that are consistent with each other of 2 to sigma, and that when combined amount to almost 4 sigma deviation. Very recently, we also had a measurement by LHCb of a sigma decay in a different hadronic environment. That's this B sub C J psi L nu bar. So this is basically the same transition, but just with a different expectative bar. And then we also saw an excess with respect to the standard model projection. So on the theory side, of course, you have to take care of the hadronic uncertainties, and this is done by different means for RD and RD star. In one case, we have very robust lattice QCD simulations that take care of these form factor uncertainties. And in the other case, we don't have lattice, but we can use experimental results in a very clever way to estimate at least the leading uncertainties. And for the subleading part, we use some theoretical arguments with very generous error bars. And the conclusion when you do this is that you cannot fill this gap between the experiment and the theory. So that's very difficult. So if this is confirmed with more data, this will be an indication of the thing. Today I'm going to talk about effective field theory for this transition. So the first step is to write the most general effective Lagrangian that's related to the B2C tau nu. And then you have, of course, this first operator, the standard model one, is just a B minus A. And then there are several others that you can write down with different effective coefficients, which can be vector, which can be scalar, which can be of thanks to phi. There are several interesting messages that I can tell you about already at this level. The first one is that it's not enough to write a Lagrangian like this, because we know that this should be heavy. We haven't seen any new particle below the electric scale, so it's a very fair assumption, and in this case that is unavoidable, that you have to impose SU2 cross U1 symmetry to this Lagrangian. And when you do so, and if you stick to only dimension 6 operators, there's this very interesting conclusion that one of these coefficients cannot be lepton flavor universality relative. So you cannot explain a difference between taus and light leptons. So that we reduce already the number of parameters that we have here. So the point is that here, this is the Lagrangian that is invalid under SU2 times U1 electromagnetic. But to generate this, you need new charged particles, and they cannot be below the electric scale. So you have to impose SU2 cross U1 inverse And if you do so, for example, this operator, it can only come from the W dipoles, W vertex at dimension 6. So you will modify the quark coupling, but the lepton one will be the same. So when you make a ratio between taus and light leptons, this is going to be cancel out. Okay, and when you try to fit data, it's interesting that there are only a few combinations of these coefficients that can actually explain the discrepancy. One very popular solution that was discussed by Andreas is a case where you have only a shift of this in the model, which is b minus a to minus a, let's say 10%. But we know that this is not the only possibility. One which is particularly interesting is the case where you have a combination of scalar and tensor operators, and that's what I'm going to talk mostly about today. And the final and most important message is that the scale of new physics to fit the discrepancy with perturbative couplings is quite low. It's at most at the TeV scale. So from that we know that electroweak Plato effects can be large. The idea of computing these electroweak loops to have further tests of this effect in Hamiltonian started with my colleagues in Padova, where they took a look at this b minus a case. And then they found this very interesting conclusion that you have very important constraints coming from z-pole observables and from universality in tau case. And they even showed that you can rule out the case where you have a minimal flavor assumption for these operators. From my point of view, I think this is interesting, not only because you can derive additional constraints, but also because you can relate them with a minimal set of assumptions, deviations in semi-leptonic decays with observables that appear in completely different sectors, such as the couplings of the Z boson or the physics of tau decays. So this can be additional tests of these anomalies that can be done with different experiments, and more than that, this can be a target to try to disentangle these possible effective coefficients that can explain the current deviations. So the question that I would like to answer in this first part of my presentation is, which observables receive contributions from the RG evolution of scalar and tensor operators? For these operators, you can fit the current data. So I showed it here in this plot in the plane GS left and GT, so tensor and scalar. I put the tau index just to make it clear that we're assuming that this has couplings to the tau lepton. And then this is the ellipse that you get from one observable. This is the one that you get from the other one. So there are basically two solutions that are viable, so these blue regions. And here there is another constraint. So on the left here, it's excluded from other regions. I can tell you more about the parameters. So the first step is, of course, to define our setup. And here what we do, the first step is to write these operators in a form that's invariant under the standard model gauge group. And to do so, you have to put the leptons and the quarks in the doublets. And these are basically the two operators that you have. So this is the scalar one, and this is the tensor one. And then when you open up these doublets, what you get is the charged part that I had in the previous Hamiltonian, and also I need some neutral operators that are unavoidably there. And the matching with my previous notation is just that GSL goes to CSL and GT goes to CT. Regarding the flavor indices here, we also need to make an assumption. And for this loop analysis, I'm going to assume that I have couplings mostly to the third generation of Fermions. That means the tau, the top, and the bottom. And then I have to say something to go from the flavor basis, where I have these operators, to the mass basis. We need an assumption, especially for the case of the right-handed Fermions. And then what I'm going to assume is that I have negligible mixing for the charged leptons here. And that's because otherwise we have very tough problems with lepton flavor violation. And second, I assume that I have a rotation between the 2 and 3 sector for that part. And the question that I would like to answer is the following: which operators are generated by the RGE effect? So this is the results I find that there are several interesting messages. So the first one is that both of these operators that couple leptons with different chiralities, they have this very peculiar property that we induce large contributions to observables which are suppressed in the standard model. The first example is the lepton dipole magnetic moment. anomalous magnetic moment. So in the standard model, I gave an example with an electroweak contribution. We know that this is proportional to the lepton mass. So you have to flip the route here to one of the external lines. But if you try to compute the same thing with the operators I'm talking about, so what you see is that since you have a coupling of a right-handed lepton with a left-handed lepton, you need to flip the route in the quark line, inside the loop. So what you get is a factor of MT instead of an lepton, and this is a huge enhancement, which would appear in this case in the dimension of the tau. The second observation that I would like to make is that you have the same thing in the Higgs physics. So Higgs to leptons, usually it's a small contribution in the standard model because the tau is very small. But here, even though you have a loop suppression, you get an enhancement by the top of your tau, and these contributions can be actually comparable. So these are the first conclusions. And the second one is that, different from the B-A operators, when you think about these scalar and tensors, you don't induce sizable multiplications of W and Z couples left. So that you can really distinguish these things by looking at different observations. So these are some of the results that we obtained. Here we select the points that can satisfy these anomalies, and then we show the correlation in the plane of the G-2 of the tau and the Higgs tau compared to the standard model. Then you have blue and green points, both are allowed, and they come from these different solutions that I showed in this plot before. And you see that for each of the solutions you have a different correlation. In the case of Higgs to tau, we can saturate the experimental bounds that we have as of now from the LHC, even though it's not so precise. And in the case of the G-2 of the tau, we can have something of 8 10 to minus 4. That's 3 orders of magnitude larger than the standard model band. As of now, the experimental limits, they're not so precise, basically because we didn't have a good reason to look for this thing. The standard model is so suppressed, so difficult to measure. But this could be a target of future experiments. For example, you can look for the G-2 of the tau by using tau relative decays at that or even in a future collider. So with this, I would like to close this first part, where the take-home message is basically that loop effects can be large when you have such a low Euclid scale. And then when you take into account these loop effects, you learn a lot, and then you have the opportunity to have alternative tests of the semi-leptonic operators in completely different environments. And I talked a bit about Higgs physics and these leptonic observers. Okay, very good. And now I'm going to move to a more model-dependent discussion. I'm going to discuss a model we propose to explain both the deviations in the charged moments and also in the neutral F-state observables. First, let me remind you very quickly what these observables are. So here we're talking about the B2K star mu compared to B2K star EE. So if we make a parallel, before we were talking about the difference between the tau and light leptons, now it's between mu's and the electrons. Before we had 3-level decay, now it's a loop-level decay. And here the situation is the following. We have measurements from a single experiment, which is LHCb, in different beams. And as you can see, you have several 2 and 3 sigma deviations that are consistent in the sense that they all go in the same direction, that you have a deficit with respect to the standard model. Of course, we need confirmation because this is a single experiment, but the results look actually quite interesting. On the theory side, what happens is that since the mu and the electron mass are negligible, most of hadronic uncertainties cancel out in this region. And actually, if the dominant source of uncertainty comes from QED corrections, as computed by the Zurich group, and that's actually quite interesting. Of course, it cannot fill the gap, but it's very surprising that you have a flavor of physics observables where there are no hadronic uncertainties. And so, if these are confirmed with more data, there will be a very clear indication of fluid physics. And now we would like to explain this with a model of fluid physics. And there are a few general comments that I can make about that. The first one that Andreas already said is that when you try to explain both anomalies, the best candidates, or the only ones that are available viable with the data that we have are the lepton parts. With all other models which are minimal, we have problems either with LHC or with some kind of flavor observations. So it's a very challenging task to actually find a model that can explain these anomalies in a minimal way. You can lepton parts, they can be vector parts, or they can be scalar. I'm not going to talk about the vectors because the scalars, they are way more minimalistic when you think in terms of the number of parameters. The vector lepton parts, they're very fine. People have proposed interesting models for that, but the problem is that in this case you need a UV completion, which is difficult to achieve without introducing many degrees of freedom. And finally, if you focus on scalar lepton parts, we know that a single scalar lepton part cannot explain all the discrepancies. So the one in 3 level, the representations which are good for the 3 level ones are bad for the loop level ones and vice versa. So actually you need to combine at least 2. So the model that we propose is the following one. We have 2 lepton parts with this representation. So these are the quantum numbers of QCD, so the triplets, and then we have a weak doublet and a weak triplet, and these are the hypercharge, 7/6 and 1/3. This is the most general UCAL interaction that you can write down for these lepton parts, where you have basically 3 UCAL matrices, and they calculate the different standard model parameters. And in the following, I'm going to assume this particular structure for these matrices, so that YR is symmetric, and that actually 2 of these matrices are connected up to a minus sign, and this will come from the UV completion that I'm going to discuss at the very end of this presentation. And then to fit data, we have a very small number of parameters. We actually have 2 masses, a minimal set of Yukawa, which is 3, and 1 angle that's very similar to the angle discussed in the first part of this presentation. When you think about the anomalies for B to C tau nu, we generate this combination of operators. So we have a scalar and tensor with this factor of plus 1/4. And for B to S mu, we have the V-A structure that's favored by current data, as explained by Andreas. An interesting point is that these anomalies, if you assume flavor blind couplings of order 1, they point at very different scales. In one case, you have 1 TeV. In another case, you have a much higher scale, which makes sense since you have 3 level, loop level observables and deviations of the same size. So you need a mechanism to explain how you can bring these things together with masses of the same order. And in our case, what happens is that this angle appears here only in the neutral decays. So this is the rotation between mass and flavor bases for the right-hand quarks. So when this value is small, you can actually suppress this observed one and have an explanation of the PV scale to both anomalies. I don't have time to talk much about the phenomenology and all the observables, but I can tell you the main conclusion is that this angle should be near pi/2, so you can achieve this suppression and you can avoid other constraints. And another novelty of the model that we propose is that this coupling it should be complex. And that will become clear when I show you next. So of course, we consider many other constraints, and I don't expect you to read this, but just to show you that when you try to build a model, there are many constraints coming from universality in the KO and B sector, and also from these loops and lepton flavor violations. So we take into account all these constraints. And these are the results. So we show the results in this plane of the effective coefficients for the B to C transition. So this GS, which is 4 times GT in our scenario, at low energy scale. We fix the mass of the lepton parts to 2 benchmark values. And then basically here you have the constraint on the real and imaginary plane for this GSL and B. And then what you get is that RD needs you to be in this region, RD star in the other one. So the only solution that you can find is when you have an imaginary couple. We cannot, actually let me explain it a bit better. So red and orange here mean that we combine these 2 constraints with the other ones that I showed in the previous slide. We can not only explain these deviations, but we also have several predictions that can be tested. And here I highlight the most interesting ones. So what I show here is the correlation between B to K, or K star new compared to the standard model value, versus B to K lepton. So lepton flavor violations in the case of B matches. And these are the regions allowed at 1 and 2 sigma. And this is the limit that we have from a value, as of now for this B to K and U decay. And then you can see that, well, the standard model will be here, right? 0 and 1. And we get a large enhancement of both of these observables. First, B2K nu is at least 50% larger than the standard model. And that is going to measure this with a 10% precision in the coming years. So it's a test of our framework. And second, and most interesting, lepton flavor violation decays become bounded both from below and above. So we find a value which is 2 times 10 to minus 7. And this is something that can really be tested with LHCb. They're working on that. And also with L2 in the coming years. Until now I have talked only about flavor constraints. But of course, when you talk about particles at the TB scale, you have to be extremely careful with LHC. There are basically 2 types of constraints that you have to take into account. So one is for the production of pair of leptoquarks that decays into pairs of quarks and leptons. So this is, for example, this PP tau-tau exclusion and this jet-jet neutrino-neutrino exclusion. And there are also constraints coming from the study of dilepton production. This is the T-channel diagram coming from the leptoquark exchange at LHC. And this excludes basically this region outside this circle. And what is interesting is that with our projections up to 100 meters per bar, the regions allowed to explain these anomalies are still are untouched by LHC. Of course, with more data, there should be also a signature of our model because they can really start probing this region. Okay, so this is what I wanted to say about how we explain these anomalies, what are the main signatures that we predict. And now let me say a few words how you can make an OV completion that embeds this to lepton formula. So, and this will be a discussion about SU5 relative unification theory. Basically what we do is that we consider 2 SU5 scalar representations of SU5, which are 45 and 50. From the 45 representation we get 1 leptoquark R2 and 1 leptoquark S3. And from the 50 we get 1 leptoquark R2. Proton decay is forbidden in our setup first, because the double leptoquark, it doesn't induce proton decay. That comes from gauging curves. With this representation, we conserve it by the number. With the other leptoquark, we have to be a bit more careful. And actually, in our setup, the only operator that can induce this proton decay comes from this contraction. So we can safely, if the coupling front of it is small, we can safely neglect it without disturbing unification or the description of the low energy phenomenology I was talking about. We need 2 representations because when you write these contractions between the fermions and the scalars, these are basically the operators that I needed from my previous discussion. So you need both, especially for the case of R2. Because from one contraction you get the couplings to the left and the leptons, but we also need the other one that comes from the other representation. And the idea is that you have these 2 R2s and 1 S3, and when you break SU5 with a 24 representation, these R2s will mix, and then in our setup we arrange the parameters so that we have a maximal mixing, and then one of these factors will be very light, and actually these couplings, you call couplings, they will be correlated, as I proposed in when I described my setup, and the other parts will be very heavy, well above our reach. And finally, we also check that this UCAL couplings, they remain perturbative if you do the one loop running up to the gut scale. Okay, that's it. So this brings me to my summary. In the first part, I was discussing the EFT implications of these anomalies, and one very interesting point is that loop corrections can be quite large, and these offer new alternatives to test viable explanations of the anomalies in charge decays. And then I point out precisely that these scalar and tensor operators can be related to Higgs decays, which are studied at the latency now, and the G-2 of the tau that could be a target of future experiments. In the second part, I discussed this model that we proposed to explain the flavor anomalies. It's a minimalist model with two flat scalar leptoquarks that's inspired by this run to unified aspiration that we had with IC5. This model can explain all the deviations, and it remains perturbative with one loop after the run up to the gut scale. And also it offers several predictions that can be tested in the future. And I think the most interesting one is precisely this decay P2K or tau, which are bounded not only from above, but also from below. So this can be, and these are sensitivities that can be achieved at LHCb and that. And finally, what I would like to be the take-home message here is that it's actually very challenging to try to explain this anomaly. And this tells a lot about the status of art of flavor physics nowadays. There are so many observables, there are so many constraints that you cannot do whatever you want, and that's good. Coming to these anomalies, of course, we need some additional confirmation. The situation is not completely clear yet, but if they're confirmed, this will be a very interesting opportunity to do data-driven model building and try to learn something about near physics by going from the bottom to the top. Thank you very much.
Thank you for your talk. So now it's time for questions and comments.
Over here, right in front. Okay. So thank you, very nice overview talk, and the angle that Andreas did nicely complementary. I'm asking first of your the benchmark points, the masses of your model to explain everything. You chose different 8 TV and 2 TV. So my question is, how flexible is your model with respect to this mass scale? Because this is conveniently within reach of LHC measurements, direct searches. I mean,
it's not very flexible actually. We can increase by a bit, but not much, because then you really mess up with the description of flavor observer. So that fact that you need a low scale really has an implication. So this could be really a target for LHC, not with 100 inverse bar, but with more data. For sure that would be very interesting.
You'll probably start seeing it already with a few hundred. You start to see signals in direct search channels already with hundreds.
Yeah, we haven't checked that, but it should be a few hundred.
Yeah, excellent. Another very short question is that these G-2 of the tau. So what kind of radical case do you have in mind that you can test at colliders, like tau to 3D or something?
So there are some proposals of doing this at value. The idea is that you have normal tau lepton decays, right? So tau to mu, neutrino, and then you can just put the insertion of a photon in the tau. And then from this you can get some sensitivity at value. But if you think about future colliders, what you need is basically about E plus E minus photon going to tau and the contribution from this side. So measuring the tau anomalous magnetic moment is completely different from the mu. Here we need to look at decays and to be very precise so that you can target that.
What branch measures do you need to, because they have a huge enhancement?
Yeah, so that I don't know exactly. I don't know, but that would be certainly something interesting to check. There are some papers about click, but I don't have the values in my mind.
There was a question over here.
Hi, so in your first project as an sort of you introduced new physics in the third family, and apart from explaining RD star, you saw a very large contribution to G-2 of tau. But you can explain RD and RD star by changing couplings to muons, and we do have, of course, G-2 problem in the muon sector. So what happens if you introduce Wilson coefficients with the second family, not the third?
Okay, so that's a very good question actually, because in the same way we have a large enhancement here for the G-2 of the tau, in principle we can have something for the G-2 of the muon. And actually, if you allow the couplings to the muons, then from the effective theory perspective, you can explain both. What I'm just not so sure about is when you try to build an actual model where you have a correlation between muons and tau couplings. So one of the examples of particles that can generate these scalar and tensor operators are leptoquarks. And in the case of leptoquarks, if you try to have both the G-2 of the muon and some deviations in the tau sector, you unavoidably induce tau to mu gamma to very large scales, except for some fine-tuned regions. So it depends a bit on on the type of particles that would induce these Wilson coefficients.
Other further questions? Okay, so this is not the case. Then thank you very much, and we move on.